Hello and welcome to today's class. For today we'll be looking at previous JAMB questions on resistors, inductors and capacitors, and we'll try to solve as many examples as we can. Before we start, let's refresh our minds on the concept of resistors, inductors and capacitors. First of all, we said a resistor is a device used to measure resistance. Of course, resistance is simply the opposition to the flow of electric current in a circuit. Now, usually for a resistor, the circuit symbol is this. So this is the circuit symbol for a resistor. This or in fact you have this. Alright, so this is your resistor circuit symbol. So we see any of this, it represents a resistor. Also for a resistor, note that when resistors are connected in series, resistor in series, that the equivalent resistance, let's say Req, equivalent resistance is equal to the sum of all the resistors up to n. As the case may be. So just simply sum them up. That's for resistors. If you have resistors in parallel, for parallel connection of resistors, we have that we'll take the inverse. So the inverse of the equivalent resistance is equal to take the inverse of each of them plus continues up to this, right? So up to the number of resistors. So if you tutored this in our previous classes, I'm just trying to refresh your mind. So this is for resistors. Number two, let's look at inductors. For inductors, your circuit symbol for an inductor is this. You have this. Alright. This is circuit symbol for an inductor. Usually resistors are represented using R. Inductors are represented using L. Now, the concept of adding in resistors in series and parallel also works for inductors. That means for inductors in series, the equivalent inductor, let's say Leq, is equal to L1 plus L2 plus keep adding them up to the last one. So that is inductors in series. For parallel connection, or in parallel, you have that the inverse of the equivalent inductor is equal to the inverse of each of them, just like this. Alright, so this is for inductors. A very important concept to note is this, that the energy stored in an inductor, is given by half Li squared. This is the energy stored in an inductor. L is inductance. And I is current. Alright. Inductance is measured in Henry, H, and then current, of course, in ampere. That's it. Alright, finally, the third one there is capacitors. Alright, so, of course, inductors are used to store electrical energy. That's a function. Capacitor is used to store electrical charges. For a capacitor, the series connection in series we have that. Now the series concept of capacitor is the parallel concept of both resistor and inductor. So that means in series, the capacitance, equivalent capacitance, is given by 1 all over Ceq is equal to 1 over C1 plus 1 over C2 plus continue. So when it comes to capacitors, to get the equivalent, I will take the inverse of it. Also, in parallel, in parallel, for capacitor, the parallel concept of a capacitor is the series concept of both resistor and inductor. That means for parallel capacitor, we have that the equivalent capacitance is equal to the sum of all that, just like this. Just simply add them up straight. And then finally, energy stored in a capacitor. Energy stored in a capacitor is E is equal to half CV squared. Please, this is the formula. This is the formula for the energy stored in a capacitor. Alright? C represents capacitance. Capacitance is in farad, and V is equal to PD, that's potential difference. Of course, measured in volts. So these are like the formula we need to play around JAMB questions on resistors, inductors, and capacitors. So we need these formulas for both resistors, inductors, and then capacitors. So we'll take some past questions and revise them together and see how we solve them. Okay, so example 1 says, from the diagram above, that's what you have there, calculate the total current in the circuit. That's all. Calculate total current in the circuit. Alright, so we have this particular circuit here. So you have this voltage, 12 voltage as a potential difference. You have 18 ohms. You have an 18 ohm resistor, 12 ohm resistor, and 6 ohm resistor. Now, from Ohm's law, we know that V is equal to IR. So we have this from Ohm's law. So if you have to solve this question, what exactly do we do? Now we have to find the total current. Now we know that for total current or current, as we have here, is equal to, if I should make current subject of the formula, I'll divide there by the resistance, divide there by resistance. This cancels this. So current is equal to voltage all over resistance. We already have voltage as 12. But the issue here is that we have, instead of just one resistance, we have 3 resistances. So my first task would be, I would have to convert these 3 resistances to a particular resistance. And that would mean I'll have to find the equivalent resistance. That's case 1. Now for this, if I look at this connection, of course, this one here is a parallel connection of resistors. This is a side-by-side connection. It becomes parallel connections. So find the equivalent of these 3 in terms of parallel connection. We said for resistance that the equivalent 1 all over R EQ, or let's say 1 over R here, is equal to 1 all over, I'm taking this as R1, 18, plus I'll take this as R2, 1 over 12, plus I'll take this as R3, 1 over 6. If I take LCM there, LCM of 18, 12, and 6, I will have that 1 all over R is equal to, my LCM becomes 36. Alright, so my LCM is 36. 36 divided by 18 gives you 2. 2 times 1 is 2. So I have 2 plus 36 over 12 is 3. 3 times 1 is 3. So I have 3 plus 36 over 6 is 6 times 1 is 6. So I have 6 there. So this is equal to, this is 5 plus 6. That gives 11 over 36. So 1 all over the equivalent resistance is equal to 11 over 36. That means from here, to get R, I'll simply invert it. If I invert it, it becomes R over 1. I'll switch this 2. It becomes R over 1. Also switch this one here. It becomes 36 over 11. So I'm having equal to 36 over 11. So that means the equivalent resistance R is equal to 36 over 11 ohms. So with this now, I've gotten the value of R. My next task is to find I. Also recall that we said from Ohm's law, the current I is equal to what there? V all over R. So let's get this done. That means I is equal to V. V is 12. That becomes 12 divided by R. R is 36 all over 11. So we have this. But I work this out. This is equal to 12 divided by 36 over 11. To solve this, the current I is equal to 12 times, we'll invert this, alright, change here to times. This is how you solve this, change here to times, invert this. So this one goes up, this comes down, becomes 11 over 36. This is now equal to 12 here 1, 12 here 3. So this now gives you 11 over 3. If I convert 11 over 3 to decimal, it gives me 3.666 etc. If I convert this to one decimal place, in one decimal place this becomes 3 points. So one decimal place gives you 7. Of course, I'm calculating for current, that becomes ampere. So my answer becomes 3.7 amperes, and that's option B. So this is how you solve this question. Alright, let's consider a second example. It says, from the diagram above, calculate the energy stored in the capacitor. That's this. Alright, so we have this diagram here. We have to find the energy stored in the capacitor. Now what we know is this. So recall that we said energy stored in the capacitor E is equal to half CV squared. Next up, pick out parameter. Before I proceed, it's important to note that the circuit symbol for a capacitor and a key or a battery or a cell, alright, they are almost alike. But the difference is this: for a capacitor, observe that the lengths are equal for this. Look at this. The lengths are equal for a capacitor. While for a cell, alright, potential difference like this, you have that one end is longer than the other. So that's the difference between these two. Alright. These two, where the two ends like this or the two lines are equal, is called a capacitor. That's a capacitor circuit symbol. But for this one here, where one is longer than the other, that becomes your cell or your battery or your potential difference, whichever one. Alright, with this now, let's solve this question. From here, I'm giving that the capacitance from here is 8 microfarad. That's equal to 8 times. Micro is 10 to the power minus 6. That becomes 10 to the power minus 6 farad. So please always do your conversion. Alright, micro is 10 to the power minus 6. Next up, I have that the potential difference V is equal to 10 volts. Alright, so let's solve this. So hence, it means that the energy E is equal to half times C. C is this, I'm using the converted value, 10 to the power minus 6 times V squared. V is 10, that gives you 10 squared. If I work this out, this is E being equal to half times 8 times, work on these two, that becomes 10. We said from indices, when two same base, when two numbers are multiplying, when they are the same, we said simply add their powers. The same number multiplying 10 and 10, add their powers. The power here is minus 6, the power here is plus 2. Minus 6 plus 2 gives you minus 4. Okay, also 2 here 1, 2 here 4. So E, the energy is equal to 4 times 10 to the power minus 4. Energy is measured in joules, so it becomes this joules. So that's the answer. Which option is that? Okay, options were not given. But anyways, this is your answer. So depending on if you have to give this in either as standard form or as decimal. As decimal, E will be equal to, so they said 4. They said times 2 to the power minus 4. From here, go back 4 times. 1, 2, 3, 4. So here, so now it's 0.0004. So that will be equal to 0.0004 joules. These two are the same thing, right? Alright, so this is how you solve this question. Alright, let's try another example. This question says the total resistance measured at PQ in the diagram above is. Alright, so here's my diagram, please. Now let me stress something here. when it comes to measuring total resistance or capacitance or inductance in figures that looks like this, now what you do is this: always start from the close end and measure up till the open end. Please don't forget, that's the pattern of solving. Start from the close end and measure up till you get to the open end. Now what do I mean? In this figure here's my close end, here it looks open. That means I'll start from this point and I'll keep solving until I get to the open end. That's how we solve problems of this nature. So where do I start from? This one here. My first task is this: observe that 1, 2, 3 are in series. Why? Because we said in series we have an end-to-end connection. It becomes this one here. This end is connected to this end. This end connected to this end. So hence 1, 2, 3. So let's first of all let's take out them. Or should we? Okay, let's just proceed. So 1, 2, 3 are in series. So I'll now resolve this one here, this one here, this one here in series. Now you may want to ask, why did I involve this one? Well, this one is kind of complex in the sense that this one, the connection on here branches to here and here. So we won't consider this one. Alright, so just take 1, 2, 3 in series. So in series, let's call this R1, R2, and R3. Okay, so R4, R5, and R6. So first up, R1, 2, 3 in series. So R1, R2, and R3 in series. So we said in series that the equivalent resistance R. So the equivalent of 1, 2, 3. So I'll call it R1, 2, 3 is equal to, since it's a series connection, I'll just add them straight. That becomes R1 plus R2 plus R3. And that's equal to R1 is 2 plus R2 is 2 plus R3 is 2. So this gives you 2, 4, 6 ohm. Now this 6 ohm is the connection for just 1, 2, 3. We are still yet to resolve 4, 5, and 6. So if I've gotten this 6 ohm as being the resistance of 1, 2, 3, where will this 6 ohm appear? It will appear at this point here. Alright, so observe the way I did this. So when I connect 1, 2, 3, we now had R1, 2, 3, that's the equivalent of 1, 2, 3 as 6 ohm. This E6 ohm will appear at this point here, such that the 6 ohm is now in parallel connection to the R4. So that means the equivalent of 1, 2, 3, which is 6 ohm, is now connected in parallel to R4. So hence, we now find the equivalent of 1, 2, 3, and 4. So hence, since this is a parallel connection, we said for parallel connection of resistors, we take inverse. So 1 all over the equivalent of 1, 2, 3, 4, which is equal to, we take inverse here, the inverse of R1, 2, 3 plus the inverse of R4. So impute values, that means the inverse of R1, 2, 3, 4 is equal to 1 all over, this value is 6. 6 plus 1 all over R4 is 3 ohms. So I have this. So 1 all over R1, 2, 3, 4 is equal to, my LCM here is 6. 6 over 6 is 1 times 1. 1 plus 6 divided by 3 is 2 times 1 is 2. So I have that. This is equal to 1 plus 2 gives you 3. So this gives me 3 in total. Also, I can break this down to each to west end. 3 here, 1, 3 here, 2. So hence 1 all over R1, 2, 3, 4 is equal to 1 all over 2. To get this value, I'll have to invert it. So I'll have that the inverse, if I invert it, this becomes R1, 2, 3, 4 all over 1, which is itself, because 2 over 1 is 2, A over 1 is A. So therefore, anything over 1 is that thing. So hence, in this case, I'll have that this all over 1 will become itself. So R1, 2, 3, 4 will be equal to, invert this becomes 2 all over 1. That's equal to 2, of course, in ohms. So I've got the value of R1, 2, 3, 4. This value now will now come this way. Alright, so see how we've now reduced our circuit from that large component up to this smaller component. This technique is called the circuit reduction technique, alright? It's used to reduce complex connections to simpler ones, as you can see. Now finally, to get my final answer, I can see that R5 is connected in series to R1, 2, 3, 4, also connected in series to R6. So hence, I will now get my final equivalent. So therefore, the equivalent resistance, this is series connection. So for series connection, I'll have that Req is equal to, decide for series, just sum the values, right? Just sum the values. So it becomes this value plus this value plus this value. So it becomes R1, 2, 3, 4. Plus R5 plus R6. So hence, the equivalent resistance is equal to R1, 2, 3, 4. This is 2. It becomes 2 plus R5 is 1. So plus 1 plus R6 is also 1. So plus 1. So hence, the equivalent resistance is equal to 2 plus 1 is 3 plus 1 is 4. So my answer is 4 ohms. Alright, so this is how you solve this question. Alright, let's try this question. This question says a circuit has a resistance of 200 ohms. Full stop. The resistance of the circuit can be reduced to 120 ohms when you have your option there. A, an 80 ohm resistor is connected to it in series. B, a 150 ohm resistor is connected to it in parallel. C, a 240 ohm resistor is connected to it in series. D, a 300 ohm resistor is connected to it in parallel. Alright, so let's analyze this question. What would it be? What do we have first? First of all, we have a resistance. Let's call this R. We said the value is 200 ohms. So we have this. Alright, let's represent the resistance of a circuit can be reduced to 120. So let's say we have a second resistance, hence I'll call this R1, I'll call this R2 to be equal to 120 this. Alright, when what happens? That's the question. At this point, the question is quite technical, but you have to understand the concept of resistance and how it works. Resistance can be added in two ways. So we said at this point you have to understand how resistors work. Alright? Resistors can be added in two ways, either in series or in parallel. When it comes to series connection, we add the values straight up. So in that case, that means if I use series connection, I will only increase the value of the resistance. For instance, I have a resistance of, let's say, 2 ohms. Let me connect a 3 ohm resistor in series. In series would mean I'm adding them straight. So it becomes 2 plus 3, that's 5 ohms. So whenever you connect resistance in series, you only increase the resistance. But if you connect it in parallel, let's say 1 all over R is equal to 1 over 2 plus 1 over 3. If I take LCM, 6 divided by 2, 3 times 1, 3, plus 6 divided by 3, 2 times 1, 2. That's equal to 5 over 6. This is the value of 1 over R. To get R, we have to invert. That becomes 6 over 5. 6 over 5 in decimal is 1.2. That becomes 1.2 ohms. So observe that the initial value has been reduced. Hence, if I want to reduce the value of a resistance, I have to connect that resistance or that resistor per se in parallel to another resistor. That means from what I have there, I have 4 options. My answer has to be a parallel connection. That means A cannot be the answer because A says in series. Also C cannot be the answer because C also says in series. So my answer is between B or D. Now I just taught you a technique, or I just taught you a technique now used in answering OBJ questions. So if I'm giving objective questions there, one of the easiest way for you to answer it is to eliminate the options that cannot even be the answer. Just like in this case, option A and C cannot be the answer. I've explained why. So it has to be a parallel connection. At this point, I have between B and D to choose. So I now have a 50% chance of getting the correct answer. So it's a technique used in answering OBJ questions. Okay, try to eliminate the option that cannot be the answer. Right, it's a good technique for answering OBJ questions. All right, let's go back to our work, please. So my option now is between B and D. So which will it be? Let's use B and C. B says let's connect a 150 ohm resistor in parallel. So this will now be, now this was my initial resistor. So if I connect 150 in parallel, what do I have? I'll take this up first. All right, so let me connect 150 to this in parallel and see if I will get this as my answer, this one here. So I'm having 1 over R is equal to 1 over 200 plus 1 over 150. I'm taking inverse to show parallel connection. So 1 over R is equal to, my LCM here is 600. Alright, 600 over 200 gives you what? 3 times 1, 3 plus 600 all over 150 gives you what there? 4. So 1 over R is equal to 3 plus 4, 7 over 600. So I have 1 over R is equal to 7 over 600. To get R, simply take inverse. So R is equal to 600 over 7. Let's punch this. 600 over 7. That gives me about 85.71 ohm, which is not what you're looking for. So this is not it. So perhaps D might be an answer, but let's confirm. So let's confirm D. 1 over R is equal to 1 all over 200 plus, for D, they said a 300 ohm resistor connected in parallel. So 1 all over, let's connect 300 in parallel. That becomes this. So 1 over R is equal to, LCM of these two should give you 600. 600 over 200 is 3 times 1 is 3 plus 600 over 300 is 2 times 1 is 2. That gives you 5 all over 600. So I have that 1 over R is equal to 5 over 600. In lowest term, this here is 1, this here is 120. So it means that 1 over R is equal to 1 all over 120. So let's get R. I will invert this, becomes R over 1, which is R is equal to 120 over 1, which is 120. So I'm having 120. So the answer is D. By connecting a 300 ohm resistor in parallel to this, we'll have the required reduced value of 120 ohm. So that's how you solve this question. Alright, so let's try another question. This question says the net capacitance in the circuit above is. So here's my circuit. If I look at this is in connection of capacitors 2 microfarad, 2 microfarad, 4 microfarad. Now I said when you're solving things of this nature, start from the closed end to the open end. For this one here, there is no real closed end and no real open end. So you have to figure out where should you start from. For this case, I'm starting from this end to this way. Now in this case, my first task is to resolve these two. If I look at these two capacitances, this and this are in parallel. So first of all, find the equivalent of these two in parallel. So let's call this C1, let's call this C2, let's call this C3. So let's resolve C1 and C2 in parallel. So what do I have there? I have that in parallel connection of capacitance, we said we sum them up directly. So C12, that's the equivalent capacitance of C1 and C2 is equal to C1 plus C2 as we discussed earlier. So this is equal to C1 is 2 plus C2 is 2. This gives you 4 microfarad. I don't really have to convert here because they are all in the same unit, so no need to convert. So I have this. So if I'm putting this one here, how would this be placed? Now, when we combine these two becomes 1 here. So I will now have this 2 becomes 1, that's this and this, straight line to this one here, this and this, then this. This one here is C3 with value 4 microfarad. This one here is the combination of these two. That's C1, 2, whose value we got here as 4 microfarad. Alright, so my final task will be to combine these two. So hence, 1 all over my equivalent or my net. When they say find net capacitance or equivalent capacitance, they are the same thing. So this is now equal to, for series connection of capacitors, we said take inverse. Becomes 1 over C12 plus 1 all over C3. So if I sum this up, this is equal to 1 over C12 is 4 plus C3, as you can see here, is also 4. Alright, with this now, I have that 1 all over CEQ is equal to the LCM of 1, 4. My LCM is 4. 4 divided by 4 gives you 1 times 1 is 1 plus 4 divided by 4 gives you 1 times 1 is 1. So I have this. If I combine this is equal to 1 plus 1 is 2 all over 4. In lowest end, 2 here, 1, 2 here, 2. That's equal to 1 over 2. So hence, 1 all over the equivalent is equal to 1 over 2. To get my equivalent, simply invert. That means CEQ over 1 is equal to, invert these 2 becomes 2 over 1. Hence, the equivalent capacitance or the net capacitance is equal to 2. My unit remains microfarad. So I have microfarad. So my answer is 2 microfarad. And that's option D, 2.0 microfarad. So that's how you solve this question. Alright, let's try another question. It says, 2 inductors of inductances 4 Henry and 8 Henry are arranged in series and a current of 10 amperes is passed through them, full stop. What is the energy stored in them? That's the question. Alright, solution. My first task is to list out my inductors. I'm giving my first inductor as 4 Henry and my second inductor as 8 Henry. Now they said they are arranged in series. And we said inductance or inductor in series is the same thing as, or is the same pattern as resistors in series. That means I'll just combine them straight up. So hence, my equivalent inductance is equal to, simply sum these two. If I sum them, I have L1 as 4 plus L2, that's 8. This gives you 12 Henry. So this is my equivalent inductance. Next exercise, you find the energy stored in them. So recall. Alright, also we're given the current I as being equal to 10 amperes. So the current is 10 amperes. So let's get this done. So recall that we said energy E is equal to half Li squared for an inductor. So hence E is equal to half times L, equivalent inductance 12 Henry times the current, that's 10 squared. So half Li squared. This is equal to half times L12 times 10 squared is 100. So let's get this done. 2 here, 1, 2 here, 6. 1 times 6, 6 times 100. That's equal to 600, of course, divided by 1, which is 600 in joules. So hence, the energy is 600 joules. That's the answer. And that's option A, 600 joules. So this question says, 3 capacitors of capacitance 2 microfarad, 4 microfarad, and 8 microfarad are connected in parallel, and a potential difference of 6 volts is maintained across each capacitor. The total energy stored is, well, let's get this done. Solution. So you're given 3 capacitors having capacitance of 2, 4, and 8 microfarad. So we said capacitors in parallel. So I'll have that in parallel, my equivalent capacitance C is equal to C1 plus C2 plus C3. For capacitors in parallel, we said sum them up straight. So I have this. So this is now equal to C1, the first thing there is 2 plus C2 is 4 plus C3 is 8. If I combine this gives me 14, the unit there, microfarad. So my equivalent is 14 microfarad. Next up, they give us potential difference or the voltage V as 6 volts. We are asked to find the energy stored in the capacitor. So recall that I said energy stored in capacitors E is equal to half CV squared. So hence, so E is equal to half times C, equivalent capacitance, 14 times 10 to the power minus 6 times V squared. V is 6, so it becomes 6 squared. So this is now equal to half times 14 times 10 to the power minus 6 times 6 squared is 36. So 2 here 1, 2 here 7. If I multiply this is equal to, let me use my calculator, 7 times 10 to the power minus 6 times 36. So I have 2.52 times 10 to the power 1, 2, 3, 4 minus 4 joules. So that's the value of this 2.52 times 10 to the power minus 4. That's option C, 2.52 times 10 to the power minus 4. So this is how you solve this question. Alright, so let's look at another question here. It says, in the circuit above, 3 resistors, 2 ohm, 4 ohms, and 12 ohms are connected in parallel, and a 12 volt battery is connected across the combination. The current flowing through the 12 ohm resistor is, alright, so we ask to find the current flowing through this one here, the 12 ohm resistor. Now, here's what you should note. Note that in a connection like this, or in parallel connection of resistors, note that the same potential difference or the same voltage flows through each of the resistors. That means the potential difference here is what you have here, 12. The potential difference here, 12 is what you have here. The potential difference, 12, is still what you have here. Also, the potential difference here is still what you have here. So this same potential difference or voltage flows across each of the capacitors here. So hence, if you have that from Ohm's law, if you have that V is equal to I R, and we say that I divided by R to get I, divided by R to get I is equal to V over R. This cancels it. So I is V over R. If you ask to find the current flowing through the 12 ohm resistor, so I will say current flowing through the 12 ohm resistor is equal to the potential difference of the 12 ohm resistor all over the resistance of the 12 ohm resistor. It's this simple. Alright, so you express this formula in terms of the 12 ohm resistor. Since we said the same potential difference or the same voltage flows across each of them, then that means V12 is equal to what I have here, 12 volts all over the resistance of the 12 ohms resistance is 12. So 12 here, 12 here, 1 all over 1. Hence, the current flowing through the 12 ohm capacitor is 1 ampere. So the answer is 1 ampere. And this is option D, 1.08. So that's your answer. This is how you solve this. Alright, let's try another question. It says, calculate the effective capacitance of the circuit above. So we have this circuit. We have to find the equivalent capacitance. Now we said for structures of this nature, we start from the closed end to the open end, which in this case is from here to this point. So how do you analyze this? Observe that 1, 2, 3 are in parallel. Alright? I would say for parallel connection of capacitance, simply add up the values. So I will have that. If I call this C1, C2, C3, C4, and C5, I'll have that the equivalent of C1 and C2 and C3 is equal to C1 plus C2 plus C3. This is parallel connection of capacitance. So that's equal to 2 plus 2 plus 2. That's equal to 6 microfarad. This value now, C1 to 3, will now come this way. So as you can see, C1 to 3 now comes this way here. So this is now in series with C4 and C5. So hence, in series, I will now have that my equivalent capacitance. Don't forget we said series capacitor, we take inverse. So it's equal to 1 all over C1, 2, 3. That's this plus this. 1 over C4 plus this. 1 all over C5. Alright, so I have this is equal to 1 over C1 to 3 is 6. So 1 over 6 plus 1 over 2 plus 1 over 3. Alright, from here, obviously the LCM is 6. LCM of 6 to 3, 6. 6 over 6 is 1 times 1, 1 plus 6 over 2 is 3 times 1, 3 plus 6 over 3 is 2 times 1, 2. So that's equal to, so I have 1 all over the equivalent capacitance is equal to 1 plus 3, 4 plus 2, 6 over 6. So this is equal to 1 over 1. We'll cancel out to give you 1 over 1. To get CEQ, take inverse. So CEQ over 1, which is CEQ, that's equivalent capacitance, is equal to 1 over 1. So hence, of course, this over 1 is itself. So the equivalent capacitance is equal to 1 over 1. And that's 1. So I have this value. So this is how you solve this. We'll take one final example and we're done for this class. Alright, so we'll take one final example for today's class. Our instruction says 3 ohm resistance, or should be resistances, are connected in parallel. What is the equivalent resistance? Quite simple. So solution. So we said 3 ohm resistances. So R1 is equal to 3. That should be ohm, no omega. R2 is 3 ohm and R3 is 3 ohm. That is said 3 ohms resistors are connected in what? Parallel. Alright. So parallel connection will have that 1 over the equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So I have that 1 over R is equal to 1 over R1 is 3 plus 1 over R2 is 3 plus 1 over R3 is 3. So 1 over R is equal to the LCM of 3 is 3. 3 over 3 is 1 times 1 plus 3 divided by 3 is 1 times 1 is 1 plus 3 divided by 3 is 1 times 1 is 1. So 1 over R is equal to 1 plus 1, 2 plus 1, 3 over 3. 3 here 1, 3 here 1. That's equal to 1 over 1. To get R, simply do inverse. So R over 1, which is equal to R, is equal to 1 over 1, which is 1 ohm. So the answer there is 1 ohm. And that is option A, 1 ohm. Alright, so this is how you tackle problems when it comes to JAMB physics question in terms of resistance, capacitance, and inductance. Alright, so this is how we solve this. Alright, see you in the next class.